Next up, we have Anita Tendler, Advancing the Solar Panel Learning Curve to Accurately Forecast a Carbon-Free Electric Grid. Anita, take it away.
Hello, my name is Anita Tendler, and I'm a PhD student in the Earth and Environment Department, and I'm also a second-year urban trainee. Today I'll be discussing the research my advisor and I, Dr. Robert Kaufman, have been working on and its policy implications. Transitioning to carbon-free energy fuels is integral to limiting greenhouse gas emissions, and electricity from fossil fuels has many public health implications such as poor air quality. Renewable technologies like solar panels are key to this transition, and the learning curve is the biggest story in solar power. The learning curve describes the trend that as more solar panels are installed globally, the price of the panels goes down. In fact, solar electricity has grown about 1,350% between 2010 and 2019, while the cost of solar panel modules, which are the square-shaped and primary component of a solar panel, have followed a downward trajectory, and this trend is expected to continue. The learning curve trend is visualized here, with electricity from solar on the x-axis and the average cost of a solar module on the y-axis. The gray line, which is the best fit line in this graph, shows a learning rate, which is the steepness of the learning curve. Prior analyses have estimated a 20% learning rate. So for each cumulative doubling of solar panels installed, the price of modules falls by 20%. But why does the learning curve matter? Well, solar panels are connected to an electric grid, so the cost to generate electricity from them must compete with fossil fuels like coal. The learning curve captures how long it will take for solar to meet the point of cost competitiveness, so energy policymakers use the learning curve to predict future solar panel cost trends. We apply an econometric modeling technique to estimate a more accurate learning curve. Our model accounts for the bidirectional relationship between growing solar installations and declining module costs. So as more solar panels are installed, module costs decline. This is the traditional learning curve. But these declining costs in turn drive solar panel installations because they become cheaper to install. Therefore, this is a solar panel feedback loop. But the solar industry is more complex than just this bivariate relationship. Global dynamics like shifts in economic activity, like GDP, and the cost of competing fuels measured through coal prices influence this feedback. So our model captures the solar panel feedback loop as well as the global dynamics that influence it. The transition to carbon-free fuels depends on the cost competitiveness of solar electricity compared to fossil fuels. The learning rate from our analysis is larger than previously estimated at 67%, which means that for each cumulative doubling of solar panels installed, the price of modules actually falls by 67%, not 20% as previously estimated. This steepens that learning curve, implying that solar is approaching the point of cost competitiveness sooner than previously thought. This point can be met even sooner through policies like a carbon tax that increase the cost of electricity from fossil fuels, which would accelerate that solar panel feedback loop, pushing solar module costs down while simultaneously supporting the growth of solar panel installations. The model estimated in our research can be used by researchers and policymakers alike to simulate how carbon-free energy policies like a carbon tax can bolster the solar industry and the technology's diffusion into the electric in order to mitigate greenhouse gases and their associated public health implications. Thank you.